Welcome to math class. Yeah, welcome to math class. Summer's over, bell is ringing. New adventures just beginning. Gonna learn and have some fun now.
Welcome. Thank you for joining me. Today we're going to be covering single transformations over using the square root function, the cubic function, and the cube root function. Now, the square root parent function, known as f of x equals the square root of x, is a subset of radical functions consisting of an endpoint, such as starting here at the origin, and extending indefinitely in one direction. Now, the square root parent function is the left half of the inverse function for the quadratic. So imagine cutting the quadratic in half and then rotating the left half clockwise about the vertex 90 degrees. So if we just took just the quadratic function, okay, and as you can see here, I've got the vertex at the origin. The axis of symmetry is at 0. It's the y line in this case here. If I took just the left half, so let's just set the dimensions on this to be x is less than or equal to 0 in this case. I'm only focusing on the left half of the function. If I took that function and I rotated it about the vertex in this case, then what we end up with is, if I rotate it 90 degrees clockwise, I end up with the square root function. So that's all this is. It's just rotating it to the right or rotating it clockwise about the vertex 90 degrees. Okay, now what I want to do is to create a visualization of the square root function. So here I have a table using Desmos. I've got x as the input column and the square root of x is going to be the output. Okay, and it's going to generate, let's take a look at what the values look like first. So if I take -4, if I try to take the square root of -4, you can see I get undefined. And that's because the square root of a negative number is imaginary. So if I try to go, say, -1, same thing. Now, once I plug in 0, I get a response. Okay, the output is going to be 0. So then if I plug in 1, the output is 1. If I plug in 4, I get an output of 2. If I go with 9, the output is 3. So you can see that I have points, and it can be any number of these points as long as it's more than 0, it looks like. So if I start at 0, start counting by 1, you can start seeing that I generate this function, right? And I can just keep going. And there we go. It's going to go off my screen. So let's take these out for a second. Now let's take a look at the actual function. Let's just have the first 4 square roots that I can see in here. Well, let's go with 16 is the next one. Okay, so if I look at the next, what I can do is set up this function here. I can grab this function, and or this moving point here, and as I move it, you'll see that it's just going through every single point on the graph until I stop at 16. Okay, so this graph, starting at the origin, moves all the way to the right until I told it to stop. And so this one here, it will just keep going on forever and ever. So let's talk about what the domain would be. The domain would be from 0, or x is greater than or equal to 0. And I set it up on here, so if you set the range here, you'll see that it's only in quadrant 1, so it's y is going to be greater than or equal to 0. Okay, then let's look at the range. The range is going to be y is greater than or equal to 0. All right, so let's take a square root function and let's plug it into Desmos. So what we're going to do is we're going to go into Desmos. We're going to take a look at what the graph in the table would look like. So for the table, let's start with some negative values. If I plug in -9, oops, I get undefined. Well, that's because the square root of a negative number is undefined. It's imaginary. So I cannot actually take the square root of a negative number. Once I hit 0, then I'm actually good. Then I can plug in 1. Square root of 1 is 1. Okay, the next one, the next perfect square is going to be 4. So the square root of 4 is 2. Next one is 9. And then the next one is 16. So you can see that I'm getting outputs whenever I have something greater than or equal to 0. So that right there is helping me define what my domain is going to be for this function. Okay. So you can see that it only happens in the first quadrant. So my domain is going to be x is greater than or equal to 0, or from 0 to positive infinity. Okay, now let's take the actual function here and let's put ourselves a point here and let's drag this point and watch what happens. As I move it to the right, that point is going through each of the other points, and you can see that it actually has more than just the 4 or the 5 points that I have on here. So what I can do is show you that. Let me take these out. Since I know I can't go less than 0, let's go with 0, then 1, and let's just watch it as it's counting from 0 all the way to 16. You can see that it is including points on the graph now. And it will keep going on and on and on. My graph is going to stop on here because I have purposely defined the limitations that it has. Now, what is the range for this? If I know that the domain is from, again, all the real numbers that are greater than or equal to 0, what about the range? The range itself is also going to be greater than or equal to 0. So 0 to positive infinity for the range. We are limited only with how large the first quadrant is. All right. I will see you in the next one. We're going to talk about the cubic function. All right. The cubic parent function is f of x equals x cubed, and it looks like a wavy looking s or upside down s, or whatever you want to call it. It is a subset of polynomial functions, and it extends indefinitely in opposite directions. So if we go to the origin, we can see that we can extend to the right and up. We can also see it extends to the left and down. So it's extending indefinitely in opposite directions. Okay. All right, so let's take the cubic function. Let's take a look at it in Desmos. Okay, so in Desmos, we have the table set up. We have x column, and then we have the x cubed column. As I plug in, let's start with some negative values here. So let's go with negative, let's go with negative 4. All right, so we get negative 64. So negative 4 cubed is negative 64. Then negative 3 cubed is negative 27. And we keep going. We can see that it's adding points to the graph, and you can see that it will continue on forever. So if I look at the domain is going to be all real numbers for x, or from negative infinity to positive infinity. The range is going to go for all real numbers as well. Goes from negative infinity to positive infinity. Okay, so what does this one look like? Let's add our, or let's take a look at our point and let's drag it. So as I start at the origin and I drag to the right, you'll see that the graph is very symmetrical. And I'll have it stop right there. Okay. And that's what the cubic function looks like. Alrighty, the cube root parent function is f of x equals the cube root of x, where the little 3 is the index of our radical expression. And it is a subset of radical functions whose ends extend indefinitely in opposite directions. So it's just like your cubic function. So the cube root parent function is the inverse of the cube parent function. If you took the cubic parent function and rotated about the origin, and reflected it over the x-axis, you would generate the cube root parent function. So let's take a look at the cube root parent function in Desmos. All right, so we have our table. We have x and the cube root of x. And then we have our function here that we'll look at here in a second. So let's take a look. Let's go ahead and throw some values in here. So think back in the square root function, we could not take the square root of negative numbers because remember they result in an imaginary result. So let's see if we can do that with cubic functions or cube root functions. So the cube root of -4 is going to be -1.587, and we're continuing there. Then let's take a look at the next one. So -3. So as you can see, I can take the cube root of negative numbers, and we'll just follow this path until I get to 4 as well. Okay, so what that's telling me is I can go all the way to the left. So my domain is going to be all real numbers as well, just like the cubic function. It goes from negative infinity to positive infinity. The range is also going to be all real numbers. It goes from negative infinity to positive infinity. If I drag the point, you can see that it's symmetrical and it is rotated as well. So as I keep going, I'll just stop right about there. And you'll see that it should be able to continue on forever. So that is the cube root parent function.